Welcome everybody. This is our 8th session in JEE Mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have made 7 videos in this series and all of those videos are available on our channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing for NEET, then you can guide them through those videos also. And if you find these videos useful, helpful, then do press the like button, share them, and subscribe to our channel. It helps a lot when you share and subscribe. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, we completed around up to 35. Now we will move ahead. Okay, so this was the last one. Question number 38, and now we will move to question number 39. Let me pen adjust pen thickness and move question to the left side. A square frame of side 10 centimeter and a long straight wire carrying current 1 ampere are in the plane of paper. I think it is plane of the paper. Starting from close to the wire, the frame moves right with constant speed of 10 meter per second. The EMF induced at the time the left arm of the frame at x is equal to 10 centimeter from the wire is. So we have to find out EMF induced in the left arm, and here it is specifically not mentioned that what will be the, we can say, either we have to find out this EMF with respect to the right arm or it is not clearly mentioned. So we will do all the things, all possible scenarios. We will solve all possible scenarios, and then we will find that what is the best one for us. Now, as current is moving in the upward direction, so magnetic field we can find out using right hand screw rule. That will be something like this. So this will be the direction of the magnetic field, or we can say in the right side of this wire, magnetic field will be into the page. So magnetic field, suppose value is B node at any point, the its specific value, as magnetic field due to a long straight wire varies as per distance. Multiply the direction vector, that will be minus K, as magnetic field is in the negative Z direction. Now here our length, for this length is in y, for this again length in y, and for these two length is in x direction. Let me mark here A, B, C, D. So length for AD and BC conductors are in the y direction, and length for CD and AB conductors are in the x direction. We know that uh, uh, we have to find induced EMF, right? So induced EMF is given by B into L cross V. Now velocity is in x direction, and we can see from here that DC, length for DC is also in x direction, and length for AB is also in x direction for both. So both for these conductors there will be no induced EMF, as length and velocity both are in the same direction. Now only left for AB and CB, AD and CB. So first let's find uh, induced EMF for the AD. So EAD will be magnetic field at AD, and as it is x distance from the wire, so magnetic field will be mu node I by 2 pi of x into its length, that is, we know side length is 10 centimeter, so 10 raised to power minus 2. Now multiply by the velocity. Velocity will be as mentioned 10. So mu node by 4 pi we know is 10 raised to power minus 7. So it will be 10 raised to power minus 7 by 2. No, sorry, not 2. We can multiply 2. So it will be 2 into 10 raised to power minus 7 into current, that is 1 ampere, divided by the distance. X is 10 centimeters, so 10 into 10 raised to power minus 2 into length 10 raised to power minus 2 into distance, sorry, velocity 10. So these all get cancelled, and we have 2 into 10 raised to power, sorry, length was 10 centimeter here, so it will be 10 into 10 raised to power minus 1. So length was here, length was 10 centimeters, so 10 into 10 raised to power minus 2, so that will be 10 raised to power minus 1. So here we will have minus 1 left, so it will be 10 raised to power minus 6 or 2 microvolt. So this is the induced EMF on the AD part. Now it is asked that induced EMF on the left arm. So we can simply just write down that this will be the induced EMF. But as this is a closed loop, so normally we have to measure this induced EMF with respect to the other point also. So we have to measure it with respect to the induced EMF in the right arm. So let's find out induced EMF in the right arm, that will be CB. Magnetic field for that one, as value of x is 10, so and side length is also 10, so distance of CB from the wire, that will be 20 centimeter. So now magnetic field is mu node twice of I by 4 pi 20 centimeter, so 10 20 into 10 by minus 2, and length is same, so it will be 10 raised to power minus 1 into our velocity 10. So this will be just 10 raised to power minus 7 into 2 into current 1 divided by 2 into 10 raised to power minus 1, and this will be 1. So 2 get cancelled, and we have 1 into 10 raised to power minus 6. So 1 microvolt. So we can say this CB is acting as a battery, of 1 microvolt, and AD is acting as a battery of 2 microvolt. And if you measure potential of D with respect to C, then it will be 2 microvolt minus 1 microvolt. So answer will be 1 microvolt. If we have been only given DA conductor like this, only this will have been given to us, then its answer will be 2 microvolt. But as this is also connected to another, it is a part of a closed loop, so we have to measure its potential with respect to the other part also. So here final answer will be 1 microvolt. Now let's move to the next question. So metallic rod of length L is tied to a string of length 2L and made to rotate with angular speed omega on a horizontal table with one end of the string fixed. If the vertical magnetic field in B is in this region, the induced EMF across the ends of the rod. So uh, we have to find EMF induced across the ends of the rod. So we can say, let's suppose that magnetic field, as already mentioned, is vertical. So suppose magnetic field is in the K direction. oh sorry, in the j direction or in the y direction. So if I draw the coordinates here, so this is suppose y direction, this is x direction, and this is z direction. So here magnetic field is along the y direction, length is along, we can say here length is along x direction, and velocity at this point, if we consider this point, velocity will be something like this. So velocity will be in the negative z direction. So to solve this type of where we have a continuous body, what we do, we normally consider a small element. So suppose this is our rod and we consider a small element of it of thickness dx at uh, distance x from the center. So induced EMF in this small element will be, that is dE, will be magnetic field B, as magnetic field is constant here, into L, length of small conductor, that will be dx, into velocity of small conductor, that will be, as it is rotating, as it is rotating with angular velocity omega, so its velocity will be, we know that v is equal to radius into omega, here radius is equal to x, so velocity will be x omega, so it will be x omega. So induced EMF in the small part will be b omega x dx. Now we can integrate it within the limits, and limits will be the starting point of this rod to the ending point of this rod. Now rod length of the rod is L and it is tied to a string of length 2L. So this is tied to a string of length 2L. So this means this point is 2L on the coordinate axis and length of rod is L. So this point is 3L. So limits will be 2L to 3L. So it will be B omega x square by 2, 3L, 2L. So B omega by 2, that will be 9L square minus 4L square. So 5 by 2 B omega L square. Option D will be the right answer here. Let's move to the next one. A coil of self-inductance L is connected at one end of two rails as shown in the figure. A connector of length L, mass M can slide freely over the two parallel rails. The entire setup is placed in the magnetic field of inductance B going into the page. As the instant t is equal to 0, initial velocity is imparted to it, and as a result it start moving along x-axis. So we give it some velocity along the x-axis. The displacement of the connector is represented by the figure. So we have to represent displacement of the connector by the any of given options. Now what happens that when we move it slightly towards the x direction, so it acquires some velocity, and that velocity is in x-axis, is along x-axis. Length of this conductor is along, we can say, y-axis, and here magnetic field is into the page. So what will happen? Magnetic field is into the page, as all of these are perpendicular, so there will be a induced EMF, and as there is induced EMF, due to induced EMF there will be a current flowing in this circuit. So finally there will be a induced EMF, and due to that induced EMF there will be a current, and as we can see that there is an inductor in this circuit. Now due to this induced current, inductor will charge, inductor will charge. Now inductor is charging and there is a current in the circuit, And as we know that when there is a current through this, when there is a current through some conductor, and that conductor is in magnetic field, so there will be a force acting on that conductor, and that force is given by B into, sorry, I into L cross B. This is the force on the conductor, and this force is such that it opposes the motion. This force is such that because this force is due to induced current, and induced current always opposes the motion. That's the Lenz's law. So the motion of this conductor, we can say our conductor AB, is towards the positive x direction. So this force will be acting such that this force will be acting such that in the negative x direction, so it can oppose the motion of this conductor. Now initially we have given it some velocity, but there is no continuous force. We have given it some velocity, but there is no continuous force, means due to this repulsive force, due to this opposite force on the conductor, velocity keeps on decreasing, because this force act as a retardation for this conductor, and due to that retardation, what happens, velocity keeps on decreasing, and finally velocity reduces to zero. Velocity reduces to zero means there is no EMF, no induced EMF, sorry. And if there is no induced EMF, then there is no current, no induced current. Means initially this conductor, initially this conductor moved slightly. Initially we given it some velocity. Due to that velocity there is induced EMF, then due to that induced EMF there is some current, and due to that current there is a opposite force acting on it, and due to that force it will stop. Now during its motion, during its motion from starting to the ending point, there was some current flowing in the circuit, and when there was some current flowing in the circuit, the inductor was charging. Now when it stops, there is no current in the circuit, so inductor will start discharging, and when inductor will discharge, there will be opposite current flowing in the circuit, and when there is opposite current flowing in the circuit, there will be opposite force acting on this inductor, on this conductor, because now direction of the current is reversed. Previously the force was towards the inside, now force will be on the outside, and again this conductor will start, we reverse the direction here. So when reverse charge, or when this inductor starts discharging, there is again opposite current flowing in the circuit. So previously this conductor was moving in the positive x direction. Now what will happen, it will start moving in the negative x direction, and it will come back to its original position. And when it come back to its original position, again this inductor has been discharged. So this process keep on happening, and this conductor will be oscillating up and down, to and fro between this position. So if we plot its displacement curve, option D will be the right answer here. Now let's move to the next question. The question has statement 1 and 2 of 4 choices given after the statement. Choose the best, describe the two statements. Self-inductance of a long solenoid with total number of turns N, radius R is less than this value. And statement 2, magnetic induction in a solenoid in statement 1 carrying current I is mu node Ni in the middle of the solenoid, but becomes less when we move towards the end. So first of all, let's look into the first statement. So self-inductance of a coil is given by, it is L mu node N square into A into L, and we can write it like this, where small n is the number of turns per unit length, so it will be capital N square into area, that is pi r square, and divided by L. So it is the same. No, we have been given that self inductance of the coil is less than this one, and if I write this here, it is pi mu node n square r square L. So this is the same value here, just pi shifted slightly here. So this statement one is false, as this is the actual value of the self inductance of the solenoid, and neither solenoid is less than this. In ideal case, self inductance is not less than this value. Now coming to the magnetic field. Now magnetic field at the center of a solenoid is given by mu node Ni, or we can write it like mu node Ni by capital L. And as we move out of the solenoid, the value of magnetic field at the edges of the solenoid is becomes half, so becomes less, and that is statement 2. So statement 2 is right, so 1 is false and 2 is true. Let's move to the next one. Boat is moving due east in region where Earth's magnetic field value is given due north and horizontal. Boat carries aerial of 2 meter long. Speed of boat is this, magnitude of induced EMF. So we know that induced EMF is BLV. So BLV, value of B is here 5 into 10 raised power minus 5, length is 2 and velocity is 1.5. So it will be 15 into 10 raised power minus 5, or we can say 0.15 millivolt. Next one. Horizontal straight wire 20-meter long extended from east to west, falling speed is mentioned, length is mentioned, right angles to horizontal component of magnetic field, and that is also mentioned. So value of induced EMF, again induced EMF is BLV. So magnetic field 3 into 10 raised power minus 5, length is 20 and velocity is 5. So 100 into 50, that will be 3 into 10 raised power minus 3, or 3 millivolt. Now let's move to next one. A rectangular loop has a sliding connector PQ of length L, resistance R ohm, moving with speed V as shown in the figure. The setup is placed in a uniform magnetic field going into the plane of paper. Three currents I1, I2 and IR. So we have to find out all the currents. So when this conductor is moving in the magnetic field, it will act as a source of induced EMF, and value of induced EMF will be given by BLV. So we can represent this whole circuit like this, that this is our resistance R, here our resistance R, and this conductor is acting as a source of EMF E, that is equal to BLV, and we have a resistance R here. Now this resistance both are these are in parallel, and if they are in parallel, then we can replace them by their parallel equivalent. So that will become, so R induced EMF, and parallel of R and R will be R by 2. So now if there is current I flowing in this arm, so there will be again same current I and same current I. So value of I will be E, that is equal to BLV divided by total resistance, that is R plus R by 2, that is 3R by 2. So I will be 2BLV by 3. So value of I will be 2BLV by 3. So here in the option, that is option B for us, only option B is matching for I. Now coming to the these two parts, that I1 and I2. Suppose this is I1 and this is I2. So this I will be shared equally in between I1 and I2, as both of the resistances are equal, and I1 will be half of I. So I1 is half of I, that is half 2BLV by 3. So BLV by, okay, we forgot R here, so it will be 3R. So again option B matches. Let's move to the next one. We have two axial solenoids made by winding thin insulated wire on pipe of cross-sectional area and length. This, if one of the solenoid has 300 turns and other 400 turns, the mutual inductance we have to find out. So we know mutual inductance is given by mu node N1 N2 into area divided by length. So 4 pi into 10 raised to power minus 7 into 300 into 400 into area, that is 10 into 10 raised to power minus 4 divided by length, that is 20. So 20 into 10 raised to power minus 2. And solving this, we will get 2.4 pi into 10 raised to power minus 4. That is option D for us. Let's move to the next one. One conducting U tube can slide inside another as shown in the figure, maintaining electrical contact between the tube. Magnetic field perpendicular is B. If each tube moves towards other at a constant speed V, the EMF induced in the circuit in terms of P. So now, as both of the tubes are moving, so we can find out relative velocity of the one. We can assume that A is at rest here and B is moving towards it. So relative velocity of B with respect to V will become 2V, and its velocity then we can assume to be 0. And now induced EMF will be BL into velocity, that is 2V. So 2BLV, and that is option C for us. Next one, metal conductor of length 1 meter rotate vertically about one of its end with angular velocity 5 radian per second. So omega is 5 given to us. If the horizontal component of earth field is this, induce EMF between the two ends of the conductor. So this is a rotating conductor, and we know that in a rotating conductor, induced EMF is BL square omega by 2. So it will be 2 into 10 raised to power minus 5 into length, that is 1 meter, so 1 square 1, and omega, that is 5 divided by 2. So 5 into 10 raised to power minus 5, or 50 microwatt. Let's move to next one. Coil having n turns of resistance R ohm is connected with galvanometer of resistance 4 R ohm. Combination is moved in T seconds from a magnetic field W1 to the W2. Induced current we have to find out. So we know induced EMF is minus d phi by dt. So induced current will be induced EMF by resistance. So it will be minus 1 by R d phi by dt. So minus 1 by R. And we have to find d phi. D phi will be the change in flux, and so it will be, suppose we have not been given area here, so let assume that area is R, sorry, area is A, and as there are n terms, so it will be n times A, and only there is change in magnetic field. So it was, initial field was W1 and final was W2. So it will be W2 minus W1, and divided by the time it took is the seconds. So it will be minus NA by RT into W2 minus W1. And now this R is the total resistance. We have coil with resistance R ohm and galvanometer with resistance 4 R ohm. So total resistance will become 5 R. So option B will be the right answer here. Area is missing in this one. So let's move to the next one. Two coils are placed close to each other. The mutual inductance of the pair of coils depends upon the rate of at which current is changing, relative position, orientation, material of the wire, current of the two wires. So mutual inductance is given by mu node N1, N2, area and length. And for when we calculate this formula, what we consider that both of the coils are overlapping on each other. So neither mutual inductance depends upon the current, neither material of the wire, and neither in the value of the current, or neither rate of change of current. It depends upon the relative position and orientation. Better the coupling, better will be the, or higher will be the mutual inductance. Next one. When the current changes from plus 2 to minus 2 in 0.5 second, 0.05 second, EMF is 8 volt. So we have to find out coefficient of self-inductance, means L we have to find out, and we know that I is equal to E is equal to L di by dt. So here we have 8 L, change in current is 4, time is 5 by 100. So that will be 20, that will be 2, L will be 1 by 10 or zero point 0.1 Henry. Option D. Last one. Conducting square of loop side L resistance R move in a plane with uniform velocity V perpendicular to one of its side. Magnetic induction B is constant in time pointing perpendicular. Induced EMF we have to find out, and we know induced EMF is velocity, magnetic field, and length. And all of these are here perpendicular. As for this conductor, there will be induced EMF only. Velocity is in x direction, length is in y direction, and magnetic field is pointing perpendicular and into the plane of paper, means perpendicular to x and y, or we can say in the z direction. So all of these three are perpendicular. So magnetic induced EMF will be BLB. So with this, I end this video here. And hopefully, whatever we have covered is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. And if you find this video useful, then do share it, subscribe to our channel. Also, uh, if you want to donate us something, then you can scan this QR code in front of your screen and donate us any amount. So with this, again, thanks for watching, and we will meet in next video.